In this video, we are going to study about a very important phenomenon which is called total internal reflection. But since in order to understand total internal reflection, we need to understand critical angle. So therefore the heading says critical angle and total internal reflection. Now get one thing very clearly, that is, this phenomenon of total internal reflection is possible only when the ray of light is coming from a denser medium and going to a rarer medium. So we talk about critical angle and total internal reflection only when ray of light is coming from denser to rarer medium. That is when the refracted ray is bending away from the normal. So first of all, let us give a look at these small dashed lines. So these small dashed lines is representing the incident ray in the denser medium. And you can see that the ray of light after refraction is bending away from the normal in the rarer medium, of course. Then after, what we do is we increase the angle of incidence. So the new incident ray is being represented by this blue line. So you can see as the angle of incidence increases, the angle of refraction also increases. And this is very much true. You further go on increasing the angle of incidence, you will see that the angle of refraction also goes on increasing. Until you reach a certain value of the angle of incidence theta c, in which case what happens is the refracted ray just grazes the surface of separation between the two media. Or in other words, in which case the angle of refraction is equal to 90 degrees. Then this value of the angle of incidence, theta c, has a special name. It is called critical angle. Therefore, critical angle, denoted by a theta c, is the angle of incidence in the denser medium for which the refracted ray grazes the surface of separation between the two media, or for which the angle of refraction in the rarer medium is 90 degrees. Next, let us see the relationship between critical angle and the refractive index. In the picture, we can see that the ray of light being incident from the denser medium, so therefore denser medium is the first medium, and the ray of light is getting refracted in the rarer medium, so therefore rarer medium is the second medium. Therefore, from Snell's law, at critical angle, the refractive index of the rarer medium with respect to the denser medium is given by mu rd, which is equal to the sine of angle of incidence divided by the sine of angle of refraction. Now for critical angle, we already know the angle of incidence is theta c and the angle of refraction is 90 degrees. Now sine 90 is 1. So therefore the refractive index of the rarer medium with respect to the denser medium is equal to sine theta c. Now from principle of reversibility of light, we know that the refractive index of the denser medium with respect to the rarer is equal to the reciprocal of the refractive index of the rarer medium with respect to the denser medium. Now since this is equal to sine theta c, so therefore the refractive index of the denser medium with respect to the rarer medium is equal to 1 upon sine of the critical angle. So this is the relationship between the critical angle and the refractive index of the denser medium with respect to the rarer. As the value of theta increases, we know the value of sine theta increases. But as sine theta increases, since it is in the denominator, what happens to the refractive index of the denser medium? The refractive index of the denser medium decreases as sine theta increases. Or in other words, higher the value of the refractive index of the denser medium, lesser will be the value of the critical angle. And let us now give a look at the factors affecting critical angle. There are two factors. The first one is the color or the wavelength of light, and the second factor is the temperature of the medium. Now we know that the refractive index of a medium is greater for violet light than the refractive index of the same medium for red light. So, since the refractive index of a medium is greater for violet light, so therefore critical angle for violet light will be lesser than critical angle for red light. Because we've already seen that greater the refractive index, lesser will be the value of the critical angle. Therefore, we conclude that the critical angle increases with the wavelength of light because red has a higher wavelength than violet. Now we also know that as the temperature of a medium increases, the medium becomes less dense. That is, the refractive index of the medium decreases with the increase in temperature. So as the refractive index decreases, we know critical angle increases. Therefore, critical angle increases with the temperature of the medium. So what are the things that we learn from this picture? What we learn is, if the angle of incidence is equal to critical angle, then the refracted ray grazes the surface of separation between the two media. If the incident ray is lesser than the critical angle, then the ray of light simply gets refracted in the second medium or in the radar medium. What if the angle of incidence is greater than the critical angle? If the angle of incidence I is greater than the critical angle, then what we see is there is no refraction taking place any longer. In fact, what happens is this incident ray of light gets totally reflected back into the denser medium following the laws of reflection, such that this angle I is equal to the angle R, which is the angle of reflection in the denser medium itself. So remember, even if this angle of incidence I is just greater than the value of the critical angle, then what happens is this phenomenon of reflection starts happening. There is no longer refraction taking place. And this phenomenon of the ray of light getting totally reflected back into the denser medium is what is called total internal reflection. The reason it's called total is because 100% of the intensity of incident light gets totally reflected back. Unlike in the case of a mirror. In case of a mirror, what happens is when a ray of light is incident on a mirror, some part of this incident light gets absorbed by the mirror. And only about 90 to 95% of the light gets reflected by the mirror. So it's not 100% of light getting reflected from the mirror. Whereas in case of total internal reflection, 100% of the light gets reflected back. So therefore, this phenomenon is called total internal reflection. So you can write this definition for total internal reflection. That is the phenomenon of a ray of light getting completely reflected back to the first medium, which of course is the denser medium. When the ray of light is being incident from a denser medium to a radar medium is called total internal reflection. Finally, now let us look at the necessary conditions for total internal reflection. There are two necessary conditions which we have already discussed about. The first one is the ray of light has to be incident from a denser medium to a radar medium. And the second is that the angle of incidence I has to be greater than the critical angle. So these are the two necessary conditions for total internal reflection to take place.